In today's lecture, we're going to cover 2.1 and 2.2, and in the next session, we're going to move on to the rest of the units. Well, in Unit 2, our focus is on probability. Let's begin. We have a preparation to begin with. To prepare for collaboration 2.1, you perform an experiment to examine if a coin is fair or not. You're going to flip a coin a large number of times. You're going to record the result with your group members in your group activity and keep track of the proportion of coin flips that result in a tail, not the head. Record your results in your notebook with your group members when you're doing the collaboration. Flip a coin 5 times and write down the outcomes of each coin flip. Record the relative frequency that we discussed before of flipping tails. After 5 flips, you can calculate the relative frequency of flipping tails by dividing the number of times you flip tails by 5. Write your answer as a decimal. Relative frequency of tail, as you remember, is going to be a fraction. On the numerator of the fraction, you have the number of successes, the number of times that you end up with a tail. You're going to divide it by the total number of tries, right? The total number of flips. So basically, when it comes to doing these experiments, when you're in your breakout room with your group members, you're going to have access to a link that directs you to a simulation. In that simulation, you can flip the coin multiple times. So for example, suppose you have 5 members in your group. 5 goes on the denominator. On the numerator, you're going to keep track of the number of tails. Suppose the number of tails might be just 2 out of 5. So each group is coming up with different results. Another group might be 0 out of 5. Another group might be 1 out of 5. Another group might be 4 out of 5, and so on. So each group is going to come up with their own fraction. Consider that at this point, if your relative frequency is a reliable estimate for the probability of flipping tails. Remember that if we repeat the 5 flips again, it's possible that the result would be the same, but we are not certain about that. On any 5 trial flip, you might flip 0, 1, 2, 3, 4, or 5, right? So flipping 5 more times might match what the result that we had before, but it's more likely to be different. If I repeat the 5 flip, it's possible the result would be the same, but it's not going to be a certain result. Continue recording your trials with your group members in the same place using the same simulation that is provided for you in your activity. At this point, you have 10 trials. Find the relative frequency after 10 trials. Now, what are you going to do? You're going to basically add up to what you did before. So if your group came up with 2 trials in the first 5 flips and you continued like 10 times and you get 3 more tails, you're going to add 3 and 2, which is going to be 5, and divide it by 10. 5 out of 10. Note that the relative frequency can change as you perform more trials. It's possible that your relative frequencies were equal after 5 and 10 trials, but most likely they were different. So what if you continue this process 15 times, right? What if you move to 25 trials? What happens to the relative frequency? So as I mentioned before, in this activity, you're going to keep track of your successes, which is the number of tails. When you're in your breakout room, one of you create a piece of paper and keep track of the number of tails. For example, in your group, you might have 3 tails in the first 5 trials. So you get 3 out of 5 or 60%. If you continue it 10 times, you get 1, 2, 3, 4, 5, 6, and 7. Now you have 7 out of 10. You get 70%. You're going to continue this process, and as you can see, for 50 times. So you're going to flip the coin 50 times and keep track of the number of tails. That's how we are coming up with a probability. When we are talking about probability and relative frequency in this case are the same. So if I ask you to find the probability that you randomly flip a coin and you end up with a tail, you're going to say that, hey, it is based on this experiment is 48%. If you repeat this process more times, like 100 times, 150 times, 200 times, 300 times, this probability is getting closer and closer to 50%, which is the law that you see in playing games. What is the probability of tossing a coin and we end up with a head? You automatically say it is 50%. Or when you're tossing a coin and you're wondering what is the probability of getting a tail, you automatically say it is 50%. But where that 50% coming from? By repeating this process multiple times, we see the probability is getting closer and closer to 50%. So this is the process that you're going to do in your breakout room and discuss it with your group members in 2.1. Let us move on to collaboration. As usual of the collaboration, we always start with some learning goals. By the end of this collaboration, you should understand that the probability of an outcome can be estimated based on its relative frequency. As the number of trials increases, the observed relative frequency of an outcome approaches. It's getting closer and closer to the probability of that outcome. By the end of this collaboration, you should be able to use a relative frequency to estimate a probability and compute proportions, everyone. Let's take a look at this example. Here we have the US Census data, American Community Survey. The United States Census Bureau collects large amounts of data about the population of the United States. The table below contains 2021 Americans Community Survey ACS data showing marital status for people of the age of 15 or more living in the United States. Note that 2 US states like Hawaii and Kansas as of 2022 have a minimum marriage age of 15. Numbers in this table are in millions of people. So when you see the number 92.7, it means 92,700,000 people. Each number is rounded to the nearest 0.1 million, which is 100,000. This is because for simplicity, so we can do the computation a little bit easier. So take a look at the table. Here, as you can see, we have a compact table give us information in each category. For example, the first category is never married. How many people? 92.7. Then you need to convert that into the million, which is 92,700,000. The next category, now married, not separated, which is 130.4. The next category is separated, which is 4.6. The next category is widowed, which is 14.8. And the final category is divorced, which is 28.8. So take a look at the total. The total is 271.3. This is the total number of people that they were surveyed for this census. You're going to answer some question. What proportion of adult population in the US is married, not separated? So take a look. They are married, not separated. So they are married, you're looking at this category. What are you going to do to find the probability? you're going to find the relative frequency. So in order to find the relative frequency, we need a numerator, we need a denominator. Since our focus is on now married, the total number of people who are now married, not separated, is 130.4 divided by what? This goes on the denominator. The total number of people who were surveyed, which is 271.3. If you do a division, calculator gives you a number around 0.481 or 48.1% of the population are now married, not separated. Another way to basically write down this number is the probability that we randomly select a person, and that person is now married is about 48.1%. So this is the probability of this event. Your event is basically you randomly select a person and that person is now married. Like you're walking on campus and you see a person and you're wondering what is the probability that person is never married, or what's the probability that person is separated, right? You can basically do the computation for each one of these categories separately. Suppose I ask you to find the probability that you see a person on campus and you're wondering what's the probability, what's the chance that person is divorced? You're finding the probability that a person is divorced. What are you going to do? You're going to do a division. 228.8 divided by the total number of people who are surveyed here, which is 271.3. Let us do the division here. 28.8 divided by 271.3, which is 0.106 or 10.6%. So that's how we find different types of probabilities for these categories, right? You can calculate other probabilities, but we need more terminologies. A college glee club has 123 members. 83 of them live on campus and 22 live in the campus adjacent apartment complex, and the remainder commute to their homes. So now let us take a look at this question. In this question, we have basically this population of 123 people. 83 live on campus. You have 22 live in the campus adjacent apartment complex, 22 apartments, and the remainder, so if you add these two numbers together, you get 83 plus 22, which is 105. You have 123 minus 105. You get 18 people, they live on their homes or they commute to campus. So this is what we have, right? This is a pie chart representing the number of people who are on campus, who live in apartment adjacent, and then 18 people who commute to campus. Are you more likely to select a student that live on campus or a student that lives in the apartments? Take a look at this. The frequency or the number of people who live on campus is the highest. So the probability or the chance that you select a person that live on campus is higher. So lives on campus because there are more people who live on campus compared to living in the apartments or even commute to campus. What is the proportion of these students that live on campus? So let me just copy and paste this one here so we don't have to go back up. Okay, here we go. What is the proportion or what is the probability of these students that live on campus? So what are we asking? We're asking what is the probability that they randomly select a student and that student live on campus. You're finding a fraction, you're finding the relative frequency. You have 83 out of 123. So let us do a division. 83 out of 123, which is approximately 0.675 or 67.5%. So if I randomly select a student and I'm wondering if that students live on campus, the chance is 67.5%. This is a relative frequency, which is exactly the same as probability. If you randomly select a student from the Glee Club, what is the reasonable value for the person to commute? So let me run a poll and ask you to calculate this. What is the probability that a person is a commuter? Give me a moment. Let me run the poll for you. What is the probability of a commuter? Please answer to the poll, everybody. You're finding the probability that you randomly select a student and that student in that club is a commuter. Please pay attention to the number of people who commute to college. That goes on the numerator. The number of folks who commute to the college, they are 18, right? You have 18 people who commute to college. So you get 18 out of 123. If you do a division, you get approximately 0.146 or 14.6%. So if you randomly select a person from the club and you're wondering, hey, what's the chance that person is a commuter? It is 14.6%. Very well. So let us move on to probability experiment of tossing a coin. Remember that in our preparation, we had an experiment, and that probability experiment was tossing a coin multiple times to calculate the probability of getting a tail. Compare your result for 10 coin flips. What was the lowest relative frequency of flipping tails in the group? So, as I mentioned before, when you're in your breakout room, you're going to reference to the piece of paper that you kept track with 50 flips, and you're going to answer the question based on that result. For 10 coins flip, what was the highest relative frequency? So basically, you're going to find the lowest relative frequency and the highest relative frequency, and you're going to compare them by doing a subtraction. When you do the subtraction, you're going to see the range of relative frequency that you had in your 10 flips. You can compare your relative frequency for 50 flips as well. You're going to do a subtraction as well, subtracting the lowest value and the highest value. For example, here if you had like the lowest relative frequency in 10 flips, if it was 2 out of 10 and the highest one was like 7 out of 10, you're going to do a subtraction like this. 7 out of 10 minus 2 out of 10, which gives you a 5 out of 10, or basically a half, or 50%. You're going to repeat this process. Remember that 50 times. And for the 50, you might have, for example, something like the lowest frequency to be 11 out of 50 and the highest frequency be 20 out of 50, then 20 out of 50 minus 11 out of 50 basically gives you 9 out of 50. If you do a division and calculate 9 out of 50, you get 18%. So basically, this is what you're trying to do. Let me move this one here. Perfect. Again, each group come up with their own work. They have a different subtraction, and they're going to enter the answer into the realize it. The law of large numbers states that as the number of trials increases, the relative frequency of a specific outcome approaches the probability. That is called the law of large numbers. If you repeat the process large enough, it means that the relative frequency and the probability is going to be similar. This means that when we talk about probability, we can talk about how frequently an outcome happens over a long period of time. We also call this long-term relative frequency. In your next assignment, you have a fun activity, pass the peaks, and basically you're going to have access to a simulation. In that simulation, you're going to have access to some peaks, and the simulation, when you select it, it's going to randomly toss a peak for you. Then you're going to keep track of the position of the peak, and you're going to repeat this process 25 times, and you're going to calculate the relative frequency of rolling a razorback. Another fun project for you again, you're going to have a link similar to what I have, and you're going to repeat the process with your group members and keep track of your process. Okay. Then you have exercise 2.1, and then you're going to move on to 2.2, which are probability types and probability rules, everybody. What are the learning goals? By the end of this collaboration, you should understand that marginal, joint, and conditional probabilities can be calculated from two-way tables. If two events are mutually exclusive, they cannot happen at the same time. If events are independent, the happening of one event make it neither more likely nor less likely that the other event happens. The probability of a set of independent events happening is the product or multiplication of the individual probabilities for each of those independent events. The probability that any set of mutually exclusive events happen is the sum of their individual probabilities. So in this lecture, we're going to go over some new terminologies and some new rules for calculating probabilities. By the end of this collaboration, you should be able to calculate marginal, joint, and conditional probabilities from a two-way table, calculate basic probabilities using multiplication rule and addition rule, identify whether two events are independent or mutually exclusive using something that we call a two-way table, find probabilities using a probability distribution and two-way table. Given the probability of an event, find the probability that the event doesn't happen. Very well. We're going to use US Census data again and work with other types of probabilities. So what do I mean by that? Take a look at this example. It's much easier to work with some examples and explain our terminologies. Here we go. US Census data. We saw US Census data before, right? It was just specifically dedicated to some specific categories. Now we're going to add more categories to our table. Remember that the United States Census Bureau collects large amount of data about the adult population of the United States. Earlier, we examined the breakdown by marital status. The two-way table below represents this data breakdown by sex as well. So as we mentioned before, the numbers in the table are in millions of people. So when we say 92.7, it means that we have 92,700,000 people. Very well. This is my table. Here I have the marital status, and it's divided up into two subcategories of male and female as well. So take a look at this. Let's just observe what's happening here. The number of people who never married in total is 92.7, which is also divided up into smaller portions. 49.5 and 43.2. If you add them together, it becomes 92.7. The next category, here you have now married, not separated. In total, we have 130.4, which is nothing but the number of male to be 66.2 and the number of female to be 64.2. Let's take a look at separated. The number of people who are separated in total is 4.6. That is divided up into 2 male and 2.6 female. Remember that these are all in compact version. The number of folks who are widowed is in total 14.8, which is divided up into 3.4 and 11.4, male and female. And finally, the number of divorced people, as we saw before, is 28.8, which is divided up into 12.2 male and 16.6 female. They also added these numbers together. They said, okay, how many male do we have in total? You have 133.3. How many female you have in total? You have 138. When you have tables like this, we say that we have a two-way table. When you have a two-way table, now you have more flexibility in answering some questions. For example, I tried to answer some probability specifically related to the margins, right? The margins includes the total. What do I mean by that? For example, suppose I'm trying to find the probability that I randomly select a person and that person is male. This is I'm trying to find the probability that I randomly, so this P represents probability. The probability of an event. The event is being male. Well, in order to find that probability, the total number of people who are participating in this survey is 271.3. How many male do I have? The number of male is 133.3. So 133.3 goes on the numerator and the total goes on the denominator. If I do a division, give me a moment, It is about 0.49 or 49%. So if I randomly select an adult in the US, what is the probability that person is male? Is 49%, right? So if I randomly select an adult in this category, what is the probability that person is married, right? What is the probability that person is married? This is what we calculated before. The number of people who are married is 130.4 divided by the total number of people, 271.3, right? We just do a division and we calculate that to be about 48%. This is what we calculated before. So being married is on the margin right here. Being a male is on the margin down here. So when we are calculating these types of probability, we're finding the marginal probability. We just focus on the margins. Very well. What else do we have? You have something that we call a joint probability. We often need to calculate probabilities that involve two outcomes, like A and B. In a two-way table, the probability of two outcomes both happening is the probability of first event and the second event. We are finding a joint probability, and the keyword for joint probability is and. Wherever you see the probability of first event and the second event, it means that you're dealing with a joint probability. Well, how do I find the joint probability? It's not that difficult. When you see and, it represents the intersection. Intersection. What do I mean by that? Hey, we're finding the probability of being male and never married. Being male is just right here. So being male, let me erase these to avoid confusion. Okay, so being male is basically this category, right? Being male. And never married is this category here. Never married. So the intersection between these two is 49.5. 49.5 goes on the numerator. 49.5 goes on the numerator. What goes on the denominator? The total number of people that we have in our census, which is 271.3. So if you do a division, just give me a moment. Let me divide these two numbers. You get about 18%. Now, suppose I ask you to find the probability that the person is female and married. Female and married. So let me run a poll and ask you to calculate this for me. What is the probability of being female and married? So please answer to the following poll. The probability that being a female and married. Which one is a correct joint probability, everyone? Being female is this category, right? Let me use a different color. Being female is this category. And now married is this category, everybody. Now married. So what is the intersection? The intersection is 64.2. 64.2 out of the total of 271.3. 64.2 out of 271.3. So let us do a division. Give me a moment. I'm using my calculator. 0.24 or 24%. So that's how we calculate something that we call joint probability. You just need to find the intersection between different categories. Okay, what else do we have? We have something that we call an independent events. When frequencies are given for values of two categorical variables in a two-way table, the joint probability, the probability of A and B, can be computed without any special rules. As you can see, you just need to find the intersection between different categories and identify what that intersection is, and that intersection goes on the numerator. And this is the total, which is your denominator. Now, the computation is easiest if you have two independent events, where the probability of one event happening doesn't depend on the happening of other event. If A and B are independent, then their joint probability is just a multiplication of their own probabilities. So the joint probability is equal to the probability of each one of them multiplied together. This is called multiplication rule for independent events. So if you have independent events, you're allowed to break down the joint probability into the multiplication of two events probabilities. Again, this is called multiplication rule for independent events. If events are not independent from each other, you're not allowed to do that. Consider the following results of a study that was described in an article entitled Caffeine as a Protective Factor in Dementia and Alzheimer's Disease. Take a look at the following table. This is a study that follows 1,409 adults for 21 years. So when it comes to statistical analysis, data science, the data over time are very important. During that time, 61 adults developed dementia. The researchers classified the research participants in now 3 categories based on their caffeine consumption. So low consumption is 0 to 2 cups per day. Medium consumption is 3 to 5 cups per day. High consumption is 6 or more cups per day. So take a look at this. This is the table of these categories. The number of people who took low caffeine is 224, but 20 of them developed dementia and 204 did not develop dementia. The number of folks with medium coffee consumption is 642, sorry. And the number of people who developed dementia is 20. The number of people who didn't develop dementia is 622. And the number of folks with high coffee consumption is 543. Out of 543, 21 develop dementia and 522 did not develop dementia. So in total, the number of people who developed dementia in this study is 61, and the number of people who didn't develop dementia in this study is 1,348. So in total, as you can see, you have 1,409 participants in this study. Suppose two people are selected at random, and it is with replacement. What's the meaning of with replacement? It means that first person is not removed from the group, they are just replaced after being selected. When the second person is selected, there is a small chance that the first person is also selected again. Because the first person is not removed, the probabilities for the second person are not changed. So the events are for sure independent from each other. So whenever you see with replacement, it means that you have independent events. So here's a keyword for you. With replacement represents independent events. So why it is important? Because when we have independent events, we can use the multiplication rule. The probability of A and B is the probability of A times probability of B. Multiplication rule applies here. So again, with replacement, meaning that you have independent events, it means that you can apply the multiplication rule. So let's take a look at the questions. It says, use the multiplication rule for independent events to compute the following probability. It says, A, calculate the probability that two people develop dementia. You're randomly selecting two people and you want to know what is the probability that both people develop dementia. We are finding the probability of the first person develop dementia and the second person develop dementia. Remember that by multiplication rule, we have the probability of A and B to be the probability of A times probability of B. So we are finding the probability of first person develop dementia multiplied by the probability of second person develop dementia. But what is the probability of a person developing dementia? Dementia. The probability of developing dementia, this is marginal probability. Why is that? The total number of people who develop dementia is 61. 61 out of 1,409, right? Now, we need to multiply these together because of multiplication rule. We have one probability, which is 61 out of 1,409 times the second probability using the multiplication rule, which is 61 divided 1,409. Let's do the multiplication here. Give me a moment. Let me use my calculator. I calculate this probability for you. This is a small probability, about 0.0019. This is a very small probability. This is 0.19%. 0.19% is different from 19%. This is a very small probability. So if you randomly select two people and both develop dementia, remember that you only have 61 people out of 1,409 developing dementia, right? So if I ask you, hey, what is the probability you randomly select three people and all of those three people develop dementia, what is that? Let me run a poll. We can extend the idea to three events as well. Again, the same multiplication rule. What is the probability that all three people develop dementia. Let me run a poll. These are independent events, everybody, because it's just with replacement. So we can apply multiplication rule. But if I ask you, hey, what is the probability? They randomly select 3 people and 3 people develop dementia. Now it's not 2 people now. You have 3 people now. You're selecting 3 people and you're wondering what is the probability all 3 people develop dementia. Now you're applying multiplication rule for 3 people, right? The probability of first person developing dementia times the probability of second person developing dementia times the probability of the third person also developing dementia. So you can extend the idea of multiplication rule to more people as well. Very well. Okay, perfect. Now the question is, if I ask you to find the probability that the first person was in low coffee consumption group and the second person was in high coffee consumption group, what is that probability? We are finding the probability of A and the probability of B. These two are also independent from each other, right? So what is the probability that a person is randomly selected from low coffee consumption group? Low coffee consumption group is this group, right? In total, you have 224. 224 out of 1,409. 224 out of 1,409 times. What is the probability that you select a person from high coffee consumption group? For the high coffee consumption group, in total you have 543. So now you have 543 divided by 1,409. So let me use my calculator and calculate this probability for you. Give me a moment. It is about 0.061, correct? So now you have about 6.1%. The probability that you randomly select 2 people and the first person is from low coffee consumption group and the second person is from high coffee consumption group is 6.1%. So far we talked about joint probability, marginal probability. Now we're going to jump into the most important probability, which is conditional probability. When 2 variables are dependent, now we are moving away from independent events. When you have independent events with replacement, it means that we are using multiplication rule. But the question is, what if we have dependent events? It's very important, everyone. Please pay attention. When 2 variables are dependent, they are not independent, obviously. This means that the probability of one event happening is influenced by the happening of the other event. So if A and B are dependent, then the probability of event B depends on a condition, whether A happens or not. If we want to know what is the probability of A and B, we multiply the probabilities again, but because B depends on A, we need the probability of B given that A happened. This is called the conditional probability. So it's not simply the probability of A times probability of B. Now you have the conditional probability of B given that A has happened. This is denoted by P, probability of B given A. So this is probability. This is probability of event B. And this vertical line you read as given and event B. For example, you go to a supermarket and you purchase some items like you buy ice cream, you buy candy, and so on. When you go to the salesperson and you try to pay, the person gives you a coupon for some other product, like a creamer. And you're wondering why I received the coupon for a creamer. Well, this is all statistics, machine learning. They basically say, okay, if a person purchase those types of ice cream, they probably going to use a specific type of creamer. So that basically is the conditional probability. Because you purchase that specific type of ice cream, they give you a coupon for a creamer. This is conditional probability. Conditional probability, you're using conditional probability in everyday life. Wherever you go, you purchase something, you use your social media app like Instagram or TikTok or other things, or when you go to Netflix, select a movie, or you go to Amazon purchasing things, they are all based on conditional probability. What is the chance? What is the probability that a person purchase this specific product based on what they purchased before? Suppose we randomly select 1% from the collection of people in the coffee dementia study. We're going to define the following events. The first event is high coffee consumption. The second event is developing dementia. We want to know what is the probability that a person develop dementia given that they consumed coffee heavily, right? We want to know, okay, if I basically drink coffee every day, 6 cups and more, what is the probability? What is the chance that I develop dementia? In order to calculate that probability, we have an interesting case. What are you going to do? In order to find the probability of B given A, you're going to form a fraction. On top of the fraction, you have the probability of B and A. Basically, you're finding the intersection. Down on the denominator, you're finding the probability of the given event. So the conditional probability of B given A is a fraction. On the numerator, you're going to find the intersection between those two events. And on the denominator, you're going to find the probability of the given event. So let's take a look at this. What is the probability of B and A developing dementia and being in high coffee consumption group? Let me just remove these to avoid any confusion here. So being in a high coffee consumption group, this is my high coffee consumption group, right? And the number of people who actually develop dementia is 21. So this is the number. This is the intersection, 21. So I have my 21 that goes on my numerator. 21 out of 1,409. Remember that. It's a probability. On the numerator, you have 21 divided by 1,409. A is the probability that you consumed coffee heavily. This goes on the denominator. The probability that you consumed coffee heavily is 543 out of the total. 543 divided by 1,409, the total number of folks who actually participated in this study. Remember that when it comes to algebra, you can cancel out the common denominator, which is 1,409. So in majority of cases, you might only see 21 out of 543. they don't include the denominators as well. Why is that? Because you can just easily get rid of the denominators. But it's 21 divided by 5, 43. Let me use my calculator. It is 0.039 or 3.9%. So this is a low chance, everyone. Low chance of developing dementia, right? If you are in high coffee consumption group, there is a low chance that you get dementia. Now my question for you is, what is the probability that a person developed dementia given that the person is in low coffee consumption group? I want you to answer to this poll based on the table that we have. What is the probability that a person developed dementia given that the person didn't drink that much of coffee? So this is probability of develop dementia given that it was in a low coffee consumption group. Very well. Please answer to this question. What is the probability that a person developed dementia given that they were in low coffee consumption group? Please pay attention. Low coffee consumption group is just right here. Develop dementia and low coffee consumption group, you get 20. On the denominator, you have the given condition. You already drank low coffee daily. So this goes on the denominator. It is 20 out of your denominator is the given condition, being in the low coffee consumption group, 224. 224. So now if I do a division, take a look. 20 divided by 224, the probability is about 0.089. 0.089. So now the chance is higher. You have 8.9%. The chance is higher now. So what's the meaning of that? Based on this study, is it better to drink coffee or not? Let me run this poll. Okay. what is your conclusion? So remember that in statistical analysis, we come up with a question, we collect data, and we have numerical analysis, right? But the conclusion is very important. Suppose you're in medical field and this is your research. How do you convey your research? What is the result of your research? Are you going to recommend people to drink more coffee, or you want to recommend people not to drink more coffee? If the people drink more coffee, the probability of developing dementia is 3.9%. If they don't drink coffee, the probability of developing dementia is higher now. It's about 8.9%. So, based on this study alone, we recommend people to drink more coffee because if you drink more coffee, it means that the probability of developing dementia is lower than when they don't drink coffee. When they don't drink coffee, the probability is 8.9%, about 9%. But if they drink coffee, the probability of developing dementia is smaller. But again, one can argue that, hey, 1,409 is not enough. We need to have more people. We need to extend this research and include more people with, more reliable results. So if it was just based on this study, when you, for example, use your social media app or you read the papers and news, they say, hey, drink more coffee, everybody. Coffee is beneficial for you. Female or male who are drinking coffee every day, 3 cups and more, 4 cups and more, it's beneficial for them. So these are usually the studies that they have. They take a look at these numbers and then they find the conditional probability. Now you know how to basically develop a research, right? Conditional probability is the one that they are referencing to give advice to people. When you go to your doctor and you're asking what is the probability, what is the chance that I develop this condition, given that my parents also have that condition, this is how they calculate those probabilities. Very important topic, very important. After conditional probability, we're using another specific probability that is called Bayes. And Bayes theorem and calculating Bayes probability make it a little bit more accurate in computing different types of probability in more complex situations. Very well. So in your breakout room, please make sure to discuss these questions. Now let us move on to without replacement. If A and B are dependent, it means that the happening of the probability of one event happening depends on the occurrence of another event. Then in this case, the multiplication rule shift its format from probability A and B, which was probability of A times probability of B, now to probability of A times the conditional probability. So again, if you have independent events, the probability of A and B is the probability of A multiplied by probability of B. If they are dependent, the probability of A and B is the probability of A times the conditional probability of B given A. That's going to be your multiplication rule for dependent events. Suppose we pick 2 people from a collection of people in the coffee dementia study above, but this time without replacement, right? This means that the first person is removed from the study before the second person is selected. So if in the first case we have 1,409, when we are removing the person, the total number reduced to 1,408. So this is the main difference. When we say without replacement, it means that the total number is now reduced. Okay, are these 2 events independent or dependent? The first person developed dementia and the second person developed dementia, right? These are dependent. Why is that? Because now I remove one person from the group. Now I change the denominator, right? They are dependent since it is without a replacement. It means that after selecting the first person, that person is removed from the group. Now we have 1,408 people in the group instead of 1,409. So that's how we identify dependent and independent events. The keyword with replacement, without replacement. Again, without replacement means that we have dependent events. Now let us compute the following. Compute the probability of A and B using the multiplication rule for dependent events. Be careful. When you select the second person, there are fewer possible outcomes, so the fraction changes. The probability of A and B, the probability of the first person develop dementia and the second person develop dementia. First, let's find the probability that the first person developed dementia. How many people actually develop dementia? Right? Let's go back to our table. The number of people who actually developed dementia in the group was 61. 61 out of 1,409. 61 out of 1,409. This is your first probability. The second probability that saying that, hey, the second person also developed dementia, given that the first person also developed dementia, and this is dependent. So now the number of people are reduced to 60 out of 1,408. That's how we calculate the multiplication rule for dependent events. We removed the first person from the group. So now the total number of people is 60 who developed dementia out of the total number of people, which was initially 1,409. Now it is reduced to 1,408. If you do the multiplication, give me a moment. Let me multiply this together for you. It's about 0.0018 or 0.18%. Very well. Let's move on to another question. Suppose we pick one person at random. We can also use the multiplication rule for dependent events to compute the probability. Okay, the first person developed dementia. Then the second event saying that the same person is in high coffee consumption group. Take a look at this. The probability of A multiplied by the probability of B given A. So what is the probability of A? You randomly select the person and that person developed dementia. We already know this is 61 out of 1,409. But what is the probability that a person is in high coffee consumption group given that the person developed dementia? Right? Take a look at this. Again, probability of B given A, saying that what is the probability that a person is in high coffee consumption group given that the person developed dementia? Take a look at this. High coffee consumption group. High coffee consumption group. Let me remove these. High coffee consumption group. given that person developed dementia, which is 21. 21, and you have the given condition, developing dementia. 21 divided by 61. 21 divided by 61. So here we go. Very good. Now, if you do the multiplication here, you can also simplify these two. You get 21 divided by 1,409. Let me just do the division here, everyone. I get 0.015 or 1.5%. Let's take a look at another example. Using the events A and B as the previous problem, it's easier to compute the probability of A and B using the following simpler rule. Write down your answer as decimal around to 3 decimal places. The probability of A and B can be written as the number of ways A and B can be both happening together divided by the total number of outcomes. So as we saw, it's going to be 21 out of 1,409, which we saw it is 0.015 or 1.5%. This was all about multiplication rule, everyone, right? For dependent events, for independent events. I expect you to ask, what if we have or what if we try to connect two events together using addition? What do I mean by that? The next rule is for computing probability of A or B. Or is the union. It's different from and, which was the intersection. Remember that when we talked about A and B, A represents intersection. When we are saying that A or B, it means that we are dealing with the union. This is different. It's going to be addition rule. It's not intersection. It's not multiplication. You have union, and you're going to use a whole different algebraic operator, which is addition. Two events are called mutually exclusive if they cannot happen at the same time. If events A and B are mutually exclusive, the probability that event A or event B happen is the sum of their individual probabilities. Very important. If you have mutually exclusive events, the events that cannot happen at the same time, the probability of A or B is the probability of A plus probability of B. Again, this is different from multiplication rule that's saying that the probability of A and B is the probability of A times probability of B. This is for independent events. For independent events, we are using multiplication rule. For mutually exclusive events, events that cannot happen at the same time, we are using the addition rule. So note the difference between these two: independent, multiplication, mutually exclusive, addition. Let's take a look at one example to feel more comfortable about what's happening here. The US Census Bureau surveyed 100,000 households where 305,688 people lived. The Census Bureau wanted to get social and economic information about people living in the United States. The two-way table below summarizes the people by the region of their primary residence in the United States who had no health insurance, and also those who have some type of health insurance. So take a look at the information. Let's just check the data, see what do we have, what categories we are looking at. The very first category is the region: Northeast, Midwest, South, and West. The number of people who doesn't have any insurance in Northeast is 6,761. In Midwest is 8,598. In South is 21,639. In West is 12,837. Whom have some health insurance? In Northeast, you have 57, and in Midwest, you have 57,408. In South, 91,498, and in West, 58,990. You also have the margin, which are the total for each category. No health insurance, 49,835. Some health insurance, 255,853. And then on the other side here, you have the total number of people who live in Northeast, the total number of people who live in Midwest, the number of people who live in South, the number of people who live in West. And then eventually, as usual, we have the total number of people who are in our survey. Very well. So people who live in Northeast cannot live in South at the same time. So these are mutually exclusive events, especially when it comes to living in a place at the same time. It doesn't have to do with dependent or independent events. These are mutually exclusive. They cannot happen at the same time. Like you are sitting here taking a class, you cannot be in, for example, Hawaii surfing, right? You are here in the class. These two events are mutually exclusive. It cannot happen at the same time. Now take a look at this. Are the events living in South and living in Midwest mutually exclusive? Yes, these are mutually exclusive events. Yes, they are mutually exclusive. They cannot happen at the same time. Okay, perfect. Since we have mutually exclusive event, we can apply the addition rule. The probability of A or B is the probability of A plus probability of B. Find the probability that a randomly selected person lives in the South or lives in Midwest. We have the keyword or, everyone. We are finding the probability of South or Midwest, which is going to be the probability of South plus the probability of Midwest. Take a look at this. What is the probability of South? How many people live in the South? You have 113, 137. Divided by the total number of people in your collection, which is 305, 688. Plus the probability of living in Midwest. How many people live in Midwest? 66,006. Divided by 305, 688. So let me find this probability using my calculator. Just give me a moment. Let me enter these numbers into the calculator. You get about 0.59 or 59%. Are the events living in the South and having no health insurance mutually exclusive? Well, they can happen at the same time. So they are not mutually exclusive. They can happen at the same time. Find the probability that you randomly select a person, that person lives in the South or has no health insurance. Take a look at this. This is going to be very interesting when we are finding the probability of not mutually exclusive events, the probability of A or B is going to be the probability of A plus probability of B. So far we have the addition minus the probability of their intersection, A and B. So this is the one that we're going to use for not mutually exclusive events. If they are not mutually exclusive, the addition rule is going to have another component minus the probability of their intersection. Very important. So in this case, the probability of south or no insurance is going to be the probability of living in the south plus the probability of no insurance minus the probability of their intersection, living in the south and having no insurance. Very well. What is the probability of living in the south? It is 113, 137 divided by 305, 688 plus. What is the probability of having no insurance? Having no insurance, how many people don't have insurance? 49,835 divided by 305, 688 minus their intersection. What is the intersection between the number of people who actually live in the south and have no health insurance? So live in the south is just right here. Have no health insurance, this is the intersection, 21, 639. Divide by the exact same denominator because we're finding out of the total. So let me use my calculator and find this addition and subtraction. Just give me a moment. The denominators are the same. You don't have to repeat the denominators. You can just basically do addition and subtraction for the numerators. You get about let me move this a little bit here so I have enough space. This is about 0.46 or 46%. Very good. So let me ask you now, what if I ask you to find the probability let me run the poll. Let's go back up here. If I ask you to find the probability of living in the south or have some insurance, what is that probability? So live in the south and have some insurance. Give me a moment so I run this poll for you. Okay, so we're finding the probability that the person live in the south and they have some insurance, right? The probability of living in the south or have some insurance. quiz answer to the poll so we can go over the algebra together. Here you have or. It means that we need to apply the addition rule. They are not mutually exclusive, right? This is the probability of A plus probability of B minus the probability of A and B. Take a look at this. What is the probability of living in the South? The number of people who live in the South is 113,137 divided by the total number of people in our survey, 305,688, plus the probability of B having some insurance. So having some insurance falls in here. Having some insurance is basically 255,853 out of 305,688 minus the probability of their intersection. So let me remove this so you don't get confused with this. And their intersection, the number of people who live in the South, right? Just right here. They have some insurance. This is the number, right? This is the intersection. Minus 91,498 divided by 305,688. Then you're going to use your calculator to find this probability. So the probability of A, probability of B, you calculate each one of them separately, minus the probability of their intersection. Very good. Okay. And one last topic for today is basically the complement. The complement of event A, which we say not A, right? Complement of event A, not A, is usually denoted by A complement, A prime, A bar. So if you have event A that's happening right here, its complement is over there. A and its complement, they are mutually exclusive. A and complement of A are mutually exclusive. The probability of event A can be written as 1 minus the probability of A complement. So the probability of A is 1 minus the probability of its complement. So if I bring this to the other side, what do I see? I see the probability of event A plus the probability of its complement is equal to 1 all the time. Question says, pick one of the individuals in the insurance data set above. Define event A to be A lives in the Northeast, Midwest, or South. Explain what the complement of A would be. So when we're writing it this way, it's saying that, hey, the probability, let's just write down the event, complement of the event, then we're going to move on to the probability. So the complement of A is the person who does not live in the first one, Northeast, or Midwest, or South. Put it in parentheses. Who doesn't live in any of these. Then I later show you that when you're finding the complement, all of them becomes AND. Compute the probability of A from the previous problem using the rule of complements. So the probability of A complement is going to be 1 minus the probability of A. Or you can write it vice versa. The probability of A is 1 minus the probability of A complement. right? So in this case, we want to find the probability using the rule of complement. What is the probability of A? The probability that a person lives in the northeast, midwest, or south. Let me remove this one and follow along with this formula. It's equal to 1 minus the probability that the person doesn't live in northeast, midwest, or south. Correct? So what's the meaning of that? It means that the person lives in the west minus the probability that the person lives in the west. So you're finding 1 minus the probability that the person lives in the west is 71,827 divided by the total. The total was 305,688. Let's find this probability using our calculator. Just give me a moment. Let me enter this into my calculator. This about 0.77 or 77%. So the probability of A that the person doesn't live in the northeast or midwest or south is 1 minus the probability of west. When you're writing down A complement, it is the probability of finding that the person lives in the west. So it simplifies our work, right? And you have your summary and then finally exercise 2.2.